The second example comes from integer factorization, and that's the basis for the RSA public key encryption scheme. So RSA being discovered in 1978 by Ron Rivest, Adi Shamir, and then Adelman. That's the Rivest, Shamir, Adelman initials in the title. So this is a public key encryption scheme whose security is based on the presumed difficulty of factoring large numbers. This is what's used in the web very widely today to secure your web transactions when you buy things securely from a website. So I'll just give you the basis for how RSA works without the details. So you all know what a prime number is, right? I hope. So a prime number is a number whose only factors are the number itself and 1. So I've listed here the first 20 or so prime numbers, 2, 3, 5, 7, 11, 13, 17, and so on. What's the next prime number in this list? 104 isn't prime. 105 is not prime. 106 is even. 107 is 107 prime. How many people think 107 is prime? We'll do it by majority. How many people think it's not prime? Okay, so it's got to be prime, right? Okay, so it's prime because you trial divide 107 by all the numbers up to some point. It has no factors except for 1 in itself, so 107 is prime. That's how you find small prime numbers. But as a fact, which I won't explain, finding large primes is a very easy task. So you can find really large primes on the computer in a matter of seconds. So for example, here's a 137-digit number, which I claim is prime. Okay? And I found this in 5 seconds on my laptop. So this is not a difficult problem for a computer to solve. The techniques used to find them are very clever. Once you have the techniques, you program them, and your computer finds large primes in a matter of seconds. So finding large primes is a really, really easy task. So what about factoring? Suppose now I pick 2 primes, P and Q, compute their product, N. N is P times Q. So my claim is that if P and Q were large primes, then factoring N would be very hard. Okay, so what do I mean by large and very hard? To make this concrete, suppose I ask you to factor 15, which is a fairly small number. What's the factorization of 15? Yeah. 3 times 5. 3 and 5 are primes. What's the factorization of 143? Anyone have a factor of 143? 11? 11 times 13? Cool. What's the factorization of 356519? Okay, so you need a calculator, right? And if you could spend a few minutes on your calculator, you would find the factorization. It's 541 times 659. Still fairly small numbers. Factor 3,053,347. That would take you a bit longer. You could write a little program to do trial division. And after some time, you would get the prime factors as follows. Okay, but my point is the larger the number n gets, the harder it is to factor. Because in the end, we don't have a very fast method for factoring numbers. We don't know of such a method. Okay, computer scientists have worked for many years in finding faster methods to factor large numbers on large computers, and we haven't been able to find very good methods. The world's record for factoring numbers was broken last year in 2009, when a group of researchers spent about 2.5 years using several hundred processors continuously, and they factored a certain challenge number, which is this one, which is 230 digits long. And here were the 2 prime factors of the number n, each being roughly 115 digits long. So this is what I mean by large number to factor. We can factor numbers of this size today, and it takes us roughly 2.5 years on a network of several hundred PCs, computers. Okay, so how might this be used in RSA? So again, the idea for RSA is for Alice to select a problem which only she knows the answer to. And the problem is the following. Alice selects 2 large prime numbers, P and Q, which remember is an easy task. So let's suppose each of P and Q is 150 digits long. This can be done in a few seconds on a computer, not by hand. She computes their product by multiplying them together to get the number n, which is now roughly 300 digits long, right? Because P and Q are each 150 digits long. All right, so Alice's public key now is the number n. This 300-digit number, while her secret key is the prime factors p and q of n. The attacker, remember, always knows Alice's public key, but to find the private key from the public key requires the attacker to factor this large number n. And factoring is believed to be a very hard computational problem. No matter how fast your computers are, it doesn't matter. No one knows how to factor numbers n that are 300 decimal digits in length. And that's the basis for RSA. Now, if Bob wants to encrypt the message for Alice, he would scramble the message using n, which is Alice's public key. I'm skipping the details. And then Alice could decrypt the message by using her primes p and q to recover the unscrambled message. And that's roughly how RSA works today. Okay, so I'm almost done. So RSA is widely used on the internet. So for example, here's Bob again, who's doing his online banking. Alice, in this case, is CIBC's online banking website. So if you have a bank account in CIBC, go to this website. It's a secured website because the HTTP ends with an S. S stands for secure. That tells you encryption is happening to protect all the data that's transmitted from your computer to CIBC's servers. Okay, so the first thing that happens when Bob visits CIBC's secure website is CIBC sends Bob her RSA number n. This number n, which is the product of two prime numbers. And here is CIBC's number n. This is CIBC's public key, a 309 decimal digit number, which I've written down here. Can you know that it's a product of two prime numbers? This number factors into two primes. The primes, presumably, only CIBC knows. Okay, so what Bob's computer does is maybe encrypt the data he wants to encrypt using the number n, sends that encrypted message over the internet, and presumably only Alice can decrypt by using her knowledge of the prime factors of this number n. So this is a challenge for computer scientists over the next few years, is to try to factor CIBC's public number n, this one right here. If you can factor this number in a few months, let's say, then you've totally broken the security of CIBC's website, because you know CIBC's secret key. Okay, so how do we know that factoring will be hard? How do we know that no one will ever be able to break this system and factor CIBC's public key, factor CIBC's large RSA number? And the answer is we really don't know if that problem is really hard. So it could be very hard, or it could be very easy. Maybe one of you tomorrow wakes up in the morning, has a clever idea for factoring. You program the idea, it works, and you can factor this large number, and you've totally broken the security of CIBC's online banking system. Okay, so CIBC relies for secure online banking on the belief that people can factor this particular 309 decimal digit number, which is quite remarkable. Okay, this is how public key is used every time you visit a secure website, which is, again, you know you are there because the URL starts with HTTPS, the S standing for secure. Any questions about this? Okay, so I've given you a glimpse of how encryption is used to secure messages, to provide confidentiality. There's many other really cool applications of this field called cryptography, besides just encryption and confidentiality. There are things like data integrity. This is when you get an email message from your friend. You think it's from your friend. How do you know it really came from your friend? How do you know no one modified the email while it was being sent over the internet to your computer? You also may want to know that the email actually came from your friend, not from an attacker who's impersonating your friend. There's very nice ways to use cryptography, like I've described here, to not just protect the confidentiality of your emails, but also prove where the email came from, that it wasn't modified during transit. There's lots of other nice, cool applications of cryptography. I'll skip them for now. I'll just leave you with the words that cryptographers and computer scientists are constantly designing new schemes to protect communications. They're also constantly analyzing old schemes like RSA. You have to constantly study the hardness of factorization to be convinced over time that it really is a hard problem. This is a constant activity by cryptographers, by computer scientists who want to maintain the security of their networks, because in the end, you always want to stay at least one step ahead of the bad guy, who's always working against you to break your systems. And that's what makes cryptography an exciting and thriving field. Okay, so I'll stop now and give you a reference where I got much of this material from. It's a book by Simon Singh called The Code Book, The Evolution of Secrecy from Mary Scott, Queen of Scots to Quantum Cryptography. It's a very readable book, accessible to senior high school students, I think grade 10, 11, 12. It's a very accessible book. So if you like what I've talked about today, you can get more details from this nice reference. Okay, so I'll take any questions you might have now.
So we have a couple of minutes for any questions here or any online questions.
Pardon me? Oh yeah, so Ed, the question was, do we teach university students how to construct and break codes? Sure, we have several cryptography classes in the CS as well as the math departments. We teach you the mathematical basis for designing and analyzing the security of codes, also how you might use them in applications to really do something good.
In fact, I did my undergrad here. 1A, first term in university, we learned the theory behind the RSA scheme. I don't know if they still do.
We still do in first year algebra. Yes.
Is encrypting, like when you write an email and you send it, is encrypting like already done?
Oh. I see. So the question is, when you send an email, is it encrypted automatically? As long as your software has encryption capabilities, then the answer is yes. But by default, email programs do not encrypt. So a priori, your email is highly insecure unless you get the right encryption software and make sure your recipient has the right secret key to decrypt. Your emails are not encrypted. So most emails today are not encrypted and therefore highly insecure. What about bank numbers? So as I said, when you visit CIBC's bank site, you'll notice that the URL becomes HTTPS and a little lock is shown closed on the browser. That means that in fact all your communications between you and your bank website is encrypted using RSA.
We have time for one more question.
What about quantum encryption?
The question is, what about quantum encryption? Okay, so that's a whole new interesting can of worms, but two quick lines. So there's things called quantum computers, which people are trying to build. They're based on quantum mechanics, which is best described as being really weird and counterintuitive. What's known is that if you can build such a quantum computer, then RSA, as I described, is totally insecure, because quantum computers can factor numbers really quickly. So if you can build a quantum computer tomorrow, security on the internet just collapses overnight, completely. What can rescue that situation, though, is the use of quantum cryptography. That's using quantum mechanics to actually do something constructive, namely design secure encryption. So there's two areas in quantum computing. One is building a computer to break encryption schemes that are used today, and using quantum mechanics to design encryption schemes which are secure even against quantum computers.
But isn't there already some quantum computers already out? Like I know there's one in Saskatoon or something like that.
Oh, the question was, don't quantum computers exist? Well, they're experimental quantum computers, but 4 or 5 have been built. They all have been built, and they factor the number 15. So it's proof of concept. So they've built these in different research groups around the world, and they can factor the number 15, which is not very impressive, but it's a proof of concept. The problem is the computers don't scale as yet to factor large numbers as the ones used in RSA today. Once they can be scaled, if they can be scaled and are scaled, then RSA just collapses overnight.
Okay, let's thank Professor Menezes.